In this video, we are going to talk about the generalized compressibility chart, and we will go over how that relates to the ideal gas law. Okay, so what we're going to do is we're going to start with something called a compressibility factor. The symbol for this is going to be a capital Z, which I'm going to make like this. Otherwise, it'll look like a 2 half the time. So that'll be the symbol I'm going to use. Now, capital Z, or this compressibility factor, it is equal to pressure times specific volume over R times T. Now in this equation, let's define all these terms. P is going to be pressure, V is specific volume, T is temperature, that's in the absolute temperature scale, and R, which we haven't seen yet, is the universal gas constant. All right, so we've got that. Now for this, if you have the Moran book, you can see table 3.1. Or at least it's table 3.1 in the version of the book I have. And if we look at that table, you will notice it's got various substances listed, and it's got the chemical formula in case you've forgotten what they are, and then it's got your R values. So here we have the SI system, here we have the English system. All right, so these are just gas constants for each of the substances that we might have to deal with. And pay attention to the units. We'll write those out in just a second. But that's what it looks like. So you can find the R values for these substances in this table. Now, if we've got other substances that are not in this table, we need to know how to find those. So let's cover that next. The equation for R is R bar over capital M. Now this R bar, let's define all these. R bar is going to be equal to 8.314 kilojoules per kilomole Kelvin, or 1.986 BTU per pound mole degree Rankine, or it can be equal to 1,545 foot-pound force per pound mole degree Rankine. And these values, you'll want to make sure you know where to find them, because you'll need them again, because not every substance we're going to use is going to be in that table. A lot of them are, but not all of them. So we're going to need these values. Now M, do y'all remember this one? We talked about this one a long time ago in chapter 1. And M was molecular weight. All right, so we covered that when we did that example where we were finding the number of moles present in a system, and then we found molecules. We talked about molecular weight. Molecular weight, that can be found in table A1. So this equation we want to highlight because you will need it again. Now, if our pressure is small relative to the critical pressure, remember the critical pressure was the pressure at the top up here. So this is the highest pressure we could have and still have the liquid and vapor together. So if our pressure of our system is small relative to this value right here, then Z, our compressibility factor, is going to be equal to 1. And to look at this, let's look at this little figure. So this is a figure in the book. This is figure 3.12. And what this shows is we've got our Z value, so PV over RT, And here is something called reduced pressure. This is basically going to be a comparison of your pressure to the critical pressure. And we'll write this down on the other sheet in just a second. So we've got P over PC, where PC is critical pressure. All right, so this is just the ratio. So you can see as this ratio, PR, that reduced pressure, as it gets small, the values all tend to be going towards 1 for Z. Right? Now we've also got these TR values. These TR values are reduced temperature. So for this, we're going to have our current temperature over the critical temperature. So it's just a ratio of basically how close we are to that critical temperature. Now you can see we've got these different symbols here. Those symbols represent these different substances. And this is what Z looks like if we plot it against the reduced pressure. So notice when this goes to 0, this always goes to 1. And for all the different substances, the values typically are about the same if you're at the same conditions. So it doesn't really change a whole lot, even though your substance might change. All right, so your Z is going to stay about the same. So that being said, we're going to be able to take that information and use it. First, let's write down all the things we just talked about on this sheet here. Let's not put if, that should be in. In figure 3.12, we see a TR number. So TR is going to be reduced temperature, and it equals temperature over TC. So this is reduced temp. This is critical temp. Now we also had that PR, that was reduced pressure, and that was pressure over the critical pressure. So it's just a ratio, basically tells you how close we are to those critical values. So now we've written all that down. Now let's review this. So the Z factor for all the gases, regardless of what the substance was, it's approximately the same at the same reduced temperature and reduced pressure values. This is basically stated in the principle of corresponding states. Now, if we are to take the data from this plot, figure 312, if you take this data, you do curve fitting on it, what we can do is get a generalized chart where we no longer have to worry about the different substances. So that's what we're going to look at next. So now, if you have the book that I have, we're going to see figures A1, A2, and A3. And one more thing, note for the reduced temperature and reduced pressure, these are not going to have units, and neither will Z. They will all be unitless. So let's make a note of that. Don't want y'all thinking I've forgotten units here. Now let's move on, and just to show you how to use this chart, we're going to do an example. So let me show you these charts. So figure A1 through A3, let's look at these. These are the curve fit charts, and this is what they look like. So notice we've gotten rid of the substances. We don't have any substances listed anymore. This is all curve fit data. It's all generalized now. Z is still on this axis. Notice the highest value is 1 here. And reduced pressure is on the x-axis. And for this table, it's going to go from 0 to 1 for reduced pressure. And then these numbers up here on the lines, those are going to be your reduced temperatures. All right, so you can see here it says TR. So you can see kind of how they change, move along the plot. Now the other ones, let's see this one right here. If we go to A2, this is what it looks like. Now this is the same thing. The only difference here is now our pressure is going to go from 0 all the way out to 10. So if you had a pressure of 7, you would need to use this table. All right. So it just gives you the expanded values for pressure, and then you still have your TR values up here at the top. And then same thing with A3. This goes from a reduced pressure of 10 out to 40. All right, and then it gives you your Z values. And again, notice when these values get small, we all kind of tend to be around the same place on these tables. So these are the tables we're going to use for this example that we're going to talk about. For this example, we're going to have air at 200 Kelvin. A pressure is going to be 132 bar, and we want to find Z. Now, in order to find Z, we have to know where to look on this table. So we have to have our reduced temperature and pressure. That'll be the first step. So reduced pressure is going to be TR equals T over TC. For air, the critical temperature is 133 Kelvin. Our current temperature is 200. Notice the units cancel, and then we get 1.504. Now next we have reduced pressure. Reduced pressure is going to be P over PC. The critical pressure for air will be 37.7 bar. Remember, these critical values are found in table A1, in case you're trying to remember where we get that from. Our current pressure is 132 bar. And that's going to give you 3.501. Now we've got our two values. We're going to go to the table, and then using this we can find Z. Reduced pressure here is 3.5, so we want to use table or figure A2 because that's the one that goes up to 10. Let's look at that one. And here's what it looks like. Our reduced temperature was 1.504, reduced pressure is 3.5. We're going to find 3.5. We're going to kind of approximate here. We obviously can't do 3.501. So 3.5 is close enough. That's this line. And then we're going to find the line that is 1.5 for reduced temperature. So right here is 1.5. Might be hard for y'all to see it, but that's what it is right there. So this solid line right here is 1.5. We just need to find the intersection of these lines. So we go up to 3.5 to the 1.5, that takes us here, and then we're going to work our way to the left to get Z. So I'm going to say that that's going to be a Z of 0.8. And that's how we use this table, or this figure. I keep calling it a table, it's really a figure. So Z here is going to be 0.8. Let's write that down. So we'll put go to figure A2, and then we're going to have reduced temperature is approximately 1.5, reduced pressure is approximately 3.5, and then Z ends up being 0.8. Now, so this would be our answer. If we look at this figure again, I just want to point out again, when our reduced pressure is small, all of our values are going to 1. So regardless of temperature, everything else, we're always going to end up at 1 when our reduced pressure here is a small number. Now, let's use that information and see what we get. So if Z is equal to PV over RT, and Z is equal to 1 when PR is small, if we plug a 1 in for that, we'll have 1 equals PV over RT. Now if you look, you get PV equals RT. Another way of writing that is P equals rho RT. Do either of these look familiar to you? If you've ever taken chemistry, they should be familiar to you. Here we've got what is the ideal gas law. Okay, so those should be familiar. So this is going to give us another equation to use. So essentially what this means, and why we're even finding Z here, because you're probably wondering what in the world we're even doing with that. If PV equals RT, if this equation here can describe a gas, then the specific internal energy depends only on the temperature. And this is going to give us our ideal gas model. So we're going to have PV equals RT. Specific internal energy is going to just be a function of temperature, and our enthalpy is also going to just be a function of temperature. All right. R will change based on your substance, but otherwise we just have temperature in here. So these three things here give us our ideal gas model. Now, so how does this take us to Z again? This compressibility chart that we were looking at, this allows you to check and see if the ideal gas model can be applied to your system. So if we want to verify that the ideal gas model works for the gas you're looking at in your system, you're going to find your Z on the compressibility chart, and Z should be 1, or very, very, very close to 1. All right, so if you get Z when you look it up after you find your reduced temperature, reduced pressure, if it's 1, ideal gas should be perfectly fine to use. And that will give us another equation to use. So that's the purpose of the compressibility chart. It allows us to see if we have ideal gas or not. Now the next section, actually this video is already getting kind of long, so let's hold off there and we'll stop this video and we'll pick it up in the next one. We'll talk more about ideal gas law. See you on the next video, guys.